All right, so median of two sorted arrays. So they give us nums1 and nums2, which are just two sorted arrays, and they want us to pretend like if we combine these two arrays into some like final sorted array, they just want the middle element, which in this case would be 2, or the median, right, which is the middle element. And in the case where say we have a even length array at the end, like after we combine both the two sorted arrays, if we have an even length array, then we would just return the two middle elements, or the average of the two middle elements. In this case, would be the 2 plus 3 would be 5, divided by 2 is 2.5. Okay, so let's just pretend that you have this magical method called get kth element, and this get kth element method, what all it's going to do is it's going to take the two sorted arrays. So it would take nums1 and nums2, which are just two sorted arrays, and it's going to return us the kth element in those two sorted arrays. So for example, if we had let's say nums1 was 1 and 4, and this nums2 was 2 and 3, so this is just two arrays, and we were to combine these two arrays into like a final sorted array, which would just be 1, 1, 2, 3, 4. If k was 2, what I'm saying there is I want the second element, and this is 1 base, not 0 base. So the second element in this final sorted array would just be this 2 here. And if say k was 1, then I would just want the first element, which would just be this 1 here. Okay, so if we had this magical method, then we could just return the middle element, right? Because we could just add up the lengths of nums1 and nums2 and then divide it by 2, and that would roughly give us the middle, and then we could just say, yeah, get us the element at that index. Or assuming that we had that imaginary final sorted array or whatever. Okay, so let's assume that we have this method, and I'm going to get into how to actually write that method. But for now, let's just assume that we have it. So let's just add up the lengths. So int length equals nums1 dot length plus nums2 dot length. Cool. And we're going to get the middle value using our get kth element method. So get kth element, pass in nums1, pass in nums2, and let's try to do length divided by 2. And let's just say that we have, let's say after we combine these two lengths, we have an array length of 3. We have an odd length array. So let's just say we have 1, 2, 3, right? So I want the second element here. So my k needs to be 2. And whatever value I pass in here, it needs to be a 2 for the second element because we want the second element in this array length of 3. Okay, so what do we have? So this length here would be 3. 3 divided by 2, so in this case length equals 3. Length divided by 2 would be 1, but this 1 is, if I pass in 1 here, that's saying that I want the first element. I don't want the first element, I want the second element. So what we're going to do is length divided by 2 plus 1. Okay, so, and then we just check if the length is odd, then just return the middle. All right, but what if it's even, right? So if the length is even, let's say we had like 1, 2, 3, 4, and so this length here would be 4. Length divided by 2 would give us, so I want to know what do we actually have here? Is this the middle left or is this the middle right that we're getting? So length divided by 2 would give us, or plus 1. So this would be 4 divided by 2 is 2, plus 1 would be 3. What I'm saying is get me the third element when I call get kth element, because I'm passing in a 3. The third element would be here. So this is actually the middle right, so I need the middle left. So what we're going to do is just say int middle left equals get kth element nums1, nums2, and just pass in length divided by 2 without the plus 1 so that we can get the middle left element. Okay, and then we just return the average of middle left plus the middle. So let me put some parentheses and divided by 2.0 to cast it to a double. So then, yes, we add the 2 up and we just take the average of them. Cool. So that was assuming that we had this magical get kth element method, but how do we actually write that get kth element method? So I'm just gonna, oh, actually, let's just make sure this works really quick. What did I, Oh, let me comment this out. This is just some, okay. So run it, submit. Okay, so it does work, assuming that we had that get kth element method. Let's get rid of that. And now let's actually talk about it. So I'm going to delete it because we're going to write it from scratch. Boom, it's gone. The entire body's gone. And let's take this. This was the example I wanted to get into. And you know what? No, let's keep the spacing here. Okay. All right, so let me comment this in. Get rid of that, get rid of this. All right, so let's get into this. So get kth element, all this method is going to do, it's going to partition our two arrays, so nums1 and nums2. It's going to partition those two arrays in a way where it will find the k smallest elements. So for example, let's say k is 5 here. So k is 5. Let's pretend this is nums1 and this is nums2. So then let's say that so let's say that I take one element from nums1. So I'm going to partition my first array like this to where I only take one element. If I only took one element from nums1, that means I have to take 4 elements from nums2. And what I'm saying here is that this is potentially my 5 smallest elements, or my k smallest elements. And if I find my k smallest elements, that just means that I got to return the kth element then, because that would give me the kth value that I'm looking for. So, but then you have to ask yourself, okay, are these actually the first 5 smallest elements in this between these two arrays? And the way that you check is you go, okay, well, is this one less than everything on the right? Well, that'll always be less than everything on the right because this is a sorted array, right? So we don't actually need to compare this, whatever's on the left, to whatever's on the right in the same array. But we have to check if this here, if anything outside our partition is smaller than us. So in this case, like, is anything out here greater than this value here? So we just have to check, is this value less than this value, or less than or equal to it, because there could be duplicates. And the answer is yeah, 1 is less than or equal to 12, right? Then we ask ourselves, okay, what about this 9 here? Is this 9 less than this 3? No, 9 is greater than 3, which means this 9 is not part of our first 5 smallest elements, or our k smallest elements. Because if there's something outside the partition that is smaller than something inside the partition, that means that we need to change our partition. We don't have the right partition because we don't have those k smallest elements that we're looking for. So what we have to do, we don't want this 9, right? We need to get rid of it. So we need, and it's too big. Because it's too big, we need to decrease this partition. So we're going to decrease it by 1. And because we decreased that partition, we have to increase the other one. So we're going to increase this partition by 1. And now we ask ourselves the same question. Do we have the k smallest element? And the way you check, is there anything outside the partition that is smaller than us? So to compare this 3 to this 9, 3 is less than 9, so we're good there. Is 8 less than 5? No, there's an element outside the partition that is smaller than something inside the partition. Therefore, we need to decrease this partition and increase the other one. Right? Because if we decrease one, we got to increase the other one because we need to keep the 5 smallest elements. So now we ask ourselves the same thing. Is this 5 less than this 8? So is there anything outside the partition that's smaller than us? This 5 is less than 8, so we're good there. Is this 4 less than 7? Cool, we're good there. So this means that we have found the k smallest elements, or the 5 smallest elements between these two arrays. So, and once you have the k smallest elements, now you just got to look at the biggest value in those 5 smallest elements. And that because the biggest value would be the kth value that we're looking for. So the biggest value is either got to be this number or this number, right? Because these are two sorted arrays, so the number furthest to the right is going to be the biggest numbers. And we just got to check, okay, which one's bigger between these two? So it's because 5 is greater than 4, 5 is the biggest element within those first 5 elements, therefore it must be our kth value. So yeah, we would just do like math.max between those two values. Okay, so now let's get into how we're actually going to binary search this. Because we're not going to linearly look for the partition. We're going to just binary search for the correct partition on the smaller array. And the reason we can just do the binary search on the smaller array is because if we know how to partition one array, we know how to partition the other one, right? Because if I take, I think I said this earlier, but like, let's say if I take one element from here, then that means I have to partition this other array like this. I have to take 4 elements from the other one. So how I partition one array determines how I partition the other one. So that's why we can just binary search for the correct partition on the smaller array. All right, so let's get into it. So in a binary search, and I'm gonna talk about like I'm gonna go into more details, but I just want to get into the code so I don't like overwhelm you with information. So let's start with our int low, right? Because we have an int low and an int high, or a left and right when we're binary searching. So our low is going to be the math dot min. No, sorry, math dot max. Actually, I should just explain this with an example really quick. Let's say that k equals 12 here. Let me comment this back in. There's 10 elements in this array here. So if there's 10 elements here, but k equals 12, well, that means we need at least 2 elements from the first array. And for example, let's say I didn't take 2 elements from the first array. Let's say I just partitioned this first array like this, where I take no elements. So if I took no elements, that means I have to take as many elements from the other array, because I need 12 elements, but the most I can take here is 10. There's only 10 elements here. So, but I need the 12 smallest elements, so therefore I need at least 2 from this array here. So that's why, yeah, so our int low is going to be math dot max of nums2.length minus k. So let's say this is, let's just pretend this is 12. Or sorry, this would be 10. Oh, I have this backwards, sorry. Sorry, okay. This would be our 12, right? So k is 12. 12 minus nums2 length is 10. So let's say this was, let me just put some numbers in there. 12 minus 10 would give us 2, but our low should be index 1. This would be our low here. So this is index 1. So what we're going to do is k minus nums2 length minus 1, because 2 minus 1 gives us 1, okay? And in case this is a negative number, right? So if, let's say k is smaller than nums2.length. So like if k was 2 and then the nums2.length is like 10, then we'll just set the low to 0, so that the low is over here. Okay, cool. So now let's do the high. Why is my index spacing off? Okay, so int high equals, so this is actually really easy. So let's just say k is 2 here. So if k is 2, that means I can take at most 2 elements from the smaller array. So that means that our high could just be here. So it would, because high is going to be exclusive in this case. So we're just saying that we can only take at most 2 elements if k is 2. So we're going to say math dot min of k and nums1.length. So if k is like really big and nums1 length is really small, then obviously high would be upper bounded by the length of the array. Okay, so now we can just binary search. So while low is less than mid, low is less than mid, low is less than high. So while low is less than high, then we can calculate our midpoint. I haven't explained what the midpoint is yet, but I'll get into it in a second. Let's just calculate what it is first. So low plus high minus low divided by 2. This is just in case there's integer overflow. But anyway, now we need, so actually let's talk about what this midpoint represents. So let me just copy paste this down here. So this would be like our nums1 here, right? So if this is nums1, then let's just say that our low is here, and this would be our high. So let's just say that it's, because it's exclusive, this is 1 past the end of the array. Our midpoint, so this would be, there's 7 elements here, so 7 divided by 2 is 3, which means this would be our midpoint here at index 3. So if this is our midpoint, what this represents is the last element in the way that I'm partitioning it. So Yeah, so this is just this midpoint just represents the index of the last element in that left partition. And nums2, we're going to calculate a midpoint for that one too. So like if we just copy paste this, and let's just pretend that let me put a space there. Let's say that we happen to partition the other array like this, then our second midpoint will be here. So that's what the second midpoint represents. It just represents the last index in that left partition of either nums1 or nums2, depending on whether it's like the midpoint or mid. Let me just type it. So mid2 would equal. Actually, yeah. So let's actually get into how we calculate mid2. So this m2, we need to this. So if we take 4 elements from here and we take 2 elements from here, that means that our k equals 6. So yeah, just pretend k equals 6. If we take 4 elements from here, this m2 needs to be at index 1, right? Because this is index 1, this would be index 0. So this would mean that this is k minus mid. So what is mid here? This would be 3. So this would be like, let's just do it over here. So this would be like 6 minus 3. This would give us 3 here, but we need 1. So what we need to do is subtract 2. So, right, because we want the 6 smallest elements, and if our midpoint is at index 3, this would be our midpoint, index 3, and k is 6, 6 minus 3 is 3, but this m2, this midpoint 2, needs to be at index 1. So we do 6 minus 3 minus 2, which would give us index 1. Okay, so let me get rid of this, and let's clean this up a little bit. And get rid of all this. Okay, so now what we need to do is let's say that I partition the arrays like this, right? So again, k equals 6. So I'm taking 4 elements from here and 2 elements from here. Well, now I actually need these values, right? Because I need to check if I have the correct partition. And how do we check if we have the correct partition? We need to check if this value here, this 7, is this less than 8? Or is this less than or equal to 8? And is this 4 less than or equal to 20? But no, I actually need these values, right, to compare them. So I'm going to call this L1. I'm going to call this R1. So left, right, and this will be L2 for the left. This will be R2 for the right. All right. And these are, so L1 is going to be the actual value here, not the index. So R1 is the value here. Okay. So let's do that. So int L1 equals, and again, so the midpoint, our midpoint is going to be here. So we can just say nums1 at the midpoint, and L2 is going to equal nums2 at mid2, because m2 will be here. And okay, so mid2 can actually end up being a negative number. And the way that happens is, let's say I took all 6 elements from this array here. So if I did this, so if k equals 6, and I take all 6 elements from nums1, then the way I have to partition this other array would be, let me just move these over here, is I would take nothing from nums2. And let me adjust this. Okay, so if I'm taking nothing from nums2, which is fine, I could take all 6 from nums1, right? But if I take nothing from nums2, what I'm going to do is I need to check if this is in bounds. So if mid2 is greater or equal to 0, then go ahead and take from nums2. But I can go ahead and take the value at that index. But if it's out of bounds, so like if it's -1, then what we're going to say is we're just going to set this to the minimum value so that we can compare. So what we're going to do is we're going to compare the minimum value, the integer minimum value, to say 40. And that'll give us a valid check or a valid input, or a valid partition, I guess. So let's do integer.min value, because all that matters is that we don't break our property of, is there anything outside the partition that is smaller than what's in the partition? And in the case where we don't have anything in the partition, then we just set it to whatever will give us a valid check when we check for like if it's less than or equal to. Okay, so int r. So now we need to do r1 and r2. So r1 is going to be nums1 at mid plus 1, right? Because it's just one index to the right. But if it's out of bounds, we got to check for that. So if mid plus 1 is less than nums1 dot length, then go ahead and take the value at that index. But if it's out of bounds, then we're just going to set this to the maximum value. So that'll happen if, like, say we have this. So R1 will just, we're taking, say, everything from nums1, but then we have nothing outside the partition. So we would end up comparing, I guess you could say you're comparing the minimum value to the maximum value, but in this, let's just say that we had, like, we partition it like this. Sorry, ASCII art is hard. Okay, so let's say I partition the second array like this. So I would compare this 3 to the maximum value here. So yeah, so there's, and this is just saying that there's nothing outside the partition here that is greater or that is smaller than what's inside my partition. So I'll go ahead and set that to whatever makes that satisfies the whole like less than or equal check. And in R2 equals, we just do the same thing. So if mid2 plus 1 is less than nums2 dot length, nums2 mid2 plus 1, and just set to the max value. So yeah, so if mid2 plus 1, so if it's in bounds of our nums2 array, then just go ahead and take the value of that index. And if it's not, then we'll just set it to the maximum value because we have nothing to compare to. There's nothing outside the partition that is smaller than us. So yeah. Now let's actually check if we have the correct value. So let's check if we have a valid partition here. So if L1, so remember what we need to do. So let me adjust this so it's like clear what we're doing here. So let's just say our partition looks like this. Yeah, this is okay. So I need to compare if this L1, if this value here is less than or equal to this value here, and I need to compare if this value here is less than or equal to this value here. And if that's true, then we have the a correct partition. So L1 is less than or equal to R1 and, or sorry, R2. So we're comparing if this value is less than or equal to this value, and L2 is less than or equal to R2. So if this value is less than or equal to, oh, R1, sorry. So yeah, if this value is less than or equal to this value, then go ahead and return the maximum of these two numbers here. Because remember, the maximum between the two must be our kth element. So math.max of L1 and L2. Cool. And if L1 is greater than R2, then, so let's say, yeah, so actually we can use this example here. So this 5 here is greater than this 4. So that means that we need to decrease this partition. We actually don't want this 5. So let's say our low is here. Let me put it up here. So if this would be our low, and let's just say that our high is here, and this would be like our midpoint. And let me just bring this in a little bit so it looks right. So let's just say that this is our midpoint, right? And this is our low, this is our high. Then if this value is greater than something that's outside the partition, then we don't want this value. So we can just bring our high over here. We can just set, because this is exclusive, we just set our high to this index here. And now we can just limit our binary search to partition, to look for a partition somewhere in this range. Okay, so what we're going to do is say high equals the midpoint. And else we can say low equals mid plus 1, because we're just adjusting. Let me see if I come up with an example. So if how can I do this? So we're saying L2 is greater than R1. Let me just, L2 is greater than R1. Then how can I'm trying to come up with something on the fly here. So 8, this will work right here. All right, let's do that. So this would be, let's get rid of this, get rid of this. Okay, so this would be our L2, and this would be our R2. So this number here, L2, is greater than R1, so we need to decrease this partition, right? And we need to increase, which means we need to increase this partition here. So what we can do is, if this is our midpoint, this was our midpoint, right? And this would say this is our low, and say our high is somewhere out here. Well, then we can just go ahead and set our low to this midpoint here. Or sorry, this midpoint plus 1. Because we're trying to increase where we're searching for this partition. So let me get rid of this. And so that's all this is doing here, is we're setting low equal to mid plus 1. And then we're just searching for the partition in somewhere in this range here. Okay, so that takes care of the binary search. But this binary search assumes that we're going to find it's looking for a value in nums1, right? So that we can, it assumes that we're going to find a value in nums1. And if it doesn't though, so like for example, let's say nums1 equals 100, 105, and 110. And let's just say that nums2 just equals 1, 2, 3, 4, 5. Okay, so so the middle element here, let's just go with 1, 2, 3, 4. So the middle element here would be this 4. So let's say so k would equal 4, right? Because we want the fourth element. So if k equals 4, we would want to return this guy, which means our partition would look like this. So we'd take nothing from nums1 and everything from nums2. And if we're taking nothing from nums1, what'll end up happening is L1 will, so this value, so L1, basically we'll keep running into this if statement here, because these values will keep being bigger than everything in R2, which, well, basically everything in the first array will continue to be bigger than everything in the right array, so we'll keep setting high to mid, and eventually low is going to equal high. And we're going to get out of this array, and which means that we just need to return nums2 at k minus 1, because we're taking nothing from nums1, and we're taking the kth element, but because this is 1 base and not 0 base, we need to do k minus 1 to get us index 3, which would here, because this would be index 0, 1, 2, and index 3. Okay, so that is the entire method. Let me just comment this stuff out, and let's run it, check that it works. What did I do wrong here? Oh, I forgot my little question mark in the ternary. What's wrong with this? Int low, math.max, k minus num2.length. Oh, nums2.length. Okay. And I do the same thing. Yeah, nums2. I can't spell. All right, I think it works. Let's submit it. Yes, it works. All right, so that's how you do this problem. I know it's a little brutal because of all the L1 and R2 stuff, but I think if you just code it like 2-3 times, like I think you can wrap your head around it. There's one last thing I want to mention. Okay, well, what's the time complexity of this? This is just the big O of the log of the minimum length of the two arrays. So like if nums1 is smaller than nums2, it'll be log of O of log of nums1's length. I can actually type it really quick. So this is going to be O of log of min of, let's just call this n and m, where uh, n is the length of nums1 and m is the length of nums2. Okay, and something I want to mention real quick. So notice I'm calling get kth element here twice, but what you could do if you really weren't happy with like calling this 2 times, then you could have get kth element return the indexes of, so like instead of returning the values here, you would return like mid and mid 2, and then you could just find and if in the case where it's an even array, to get this, instead of calling get kth element again, you could do mid, you could just basically do mid plus 1 and mid 2 plus 1 to get that right element and to get the maximum between the two. But it's just food for thought. Like you could, I'm perfectly happy with just calling get kth element twice. But the idea is here that you would just return the indexes, because if this returns the middle right element, oh sorry, yeah, if this returns the middle right element, you'd actually have to return, you could get the indexes minus 1 from that. Hopefully that makes sense a little bit. But yeah, anyway, that's how you do this problem, or that's how I would do this problem. And it's good because I feel like you can reuse this for at least one other problem, because there's actually a problem called get kth element or whatever. But not on LeetCode, it's on Geek for Geeks or whatever. But anyway, yeah, have fun guys, and you can like the video and subscribe if you want. Cool, bye.